Hello, everyone, and thank you very much for tuning in today. My name is Derek, and today I'm joined by Josh, Eric, and Chris to present our findings for the optimal design of the hydroelectric energy storage system. Today, we will be discussing the team's general design philosophy and factors that were considered when leading to the final model, as well as demonstrating that model and sharing the results that we believe to be the most cost-effective solution to the problem. To quickly recap that problem, the team was tasked with finding the optimal configuration of materials and land use for construction of a hydro storage system that is powered by solar cell energy production. The team went about this task by first developing a model of the energy of the system based off of the principles of the universal accounting equation, which can be seen on the left side of your screen. The universal accounting equation states that final minus initial is equal to input minus output plus generated minus consumption. But what exactly does this mean? Well, based off of the project description, the team knew that the requested output of the system was 120 megawatt hours. And it was also determined that for the model, the team could assume that the final and initial energies of the system would be zero, and that the system would not generate any additional energy as well. Thus, the only factors that Team 67 were concerned with were the factors that would consume energy and how much energy would have to go into the system to produce the desired output of 120 megawatt hours. In a perfect system, the energy in would equal the energy out, and the system would be 100% efficient. However, such a system in reality is impossible, so the team needed to consider effects that would cause the energy to be consumed by the system, such as turbine and pump efficiencies, pipe friction, and pipe bend loss. All of these factors would be design choices selected by the team and would combine together to form the entirety of the consumed section, leading to the final equation for input energy, E in, that you can see on your screen. The final problem for the energy system was to determine the mass, as many of the equations for energy loss involve mass. With the assumption of zero mass loss, the group determined that the mass would be entirely dependent on the draining and filling time of the system, which would add in two new design choices for the team to consider. Although these were what ultimately made it into the system, there are plenty of other factors for the team to consider as well.
Although the configuration of the system contributed the most to the design choices of Team 67 and affected the efficiency of the design the most, additional factors played into our design process as well. At the beginning of engineering Team 67's design process, we thought through the different internal factors that would affect the efficiency of the design. Throughout this process, we developed an understanding of what we needed to consider in our final model of efficiency. In the end, the team chose to ignore several factors as they seemed unlikely or affected the efficiency of the system very little. The first of these was the possibility of large animals or humans falling into the reservoir. However, this possibility seemed unlikely. The reservoir would be at least 15 feet tall, therefore an animal or human would have to climb up the wall in order to fall into the reservoir, an event that seems unlikely. Our engineering team therefore decided to ignore this possibility. Additionally, our team considered the effect of evaporation of water within the system. After researching this topic, we found that even given the worst evaporation environment in the United States, evaporation would account for a decrease in efficiency of less than 0.05%. Therefore, we decided to ignore this factor in our model. Also, Team 67 considered the external circumstances that would affect our system when considering which zone to build in. Early on, we unanimously decided not to build on Site 2 because of the American Indian burial grounds there within. Historically, the United States has treated American Indians poorly. In a desire to break this trend, we decided to ignore the possibility of building on Site 2, despite the possible sacrifices of cost and efficiency that would have to be made. After further considering the different potential building zones, our team also decided to not build on Zone 3 because of the concerns surrounding erosion in this location. Given that the reservoir would rest atop a hill in order to maximize energy storage, any erosion would have a profound influence on the integrity of the system. Shifting of the surface underneath the reservoir because of erosion would cause cracks in the walls and floors of the system, which would allow water to leak from the reservoir, leading to a decrease of efficiency. Additionally, these cracks would increase the likelihood of catastrophic failure, in which the walls of the reservoir would collapse. Not only would this failure cost a great deal, it would damage the environment by altering ecosystems, and it would endanger the community relying on the power. Team 67 considered several ways of combating erosion, including the planting of additional foliage to help prevent erosion. However, this would cost additional money, and this solution would take years to develop, since it can take years for the root system of a tree to grow. In the end, Zone 3 simply proved infeasible.
For the recommendation of this design, the selection is based on the code created by Team 67 that optimizes 300,000 different configurations of parts from the parts catalog by calculating the efficiency and cost of each option. These top graphs represent the statistics of all the options calculated by the code, and the black dot represents the selected configuration. The team ultimately selected the best option by finding the configuration with the lowest cost per efficiency. We found out what this option was by finding the minimum of this first graph. As you can see from the second graph, the selected point is very low cost and high efficiency compared to the other options. The bottom two graphs show the cost and efficiency of the options. As you can see, the cost is near one of the minimums of the graph, and the efficiency is also near the peak. The final specifications of the selected configuration are shown in this table here. The code selected a pump and turbine that are of the highest quality, so they have very little efficiency losses, whereas the pipes and fittings are of a medium quality with the largest 3-meter diameter. These selections made by the code fit the constraints of the site well, because Site 1 has a lower elevation and a short run of pipes, so most of the losses will come from the pump and the turbine, so more money should be spent on the pump and the turbine than on the bends and the fittings. Plugging these part selections into the model results in a calculated 10 hours of fill time, 10 hours of empty time, a total efficiency of 0.8044, and a required input of 149.2 megawatt hours to get an output of 120 megawatt hours. And the total calculated cost for the proposed projects is $427,565. Team 67 decided that selecting a configuration based on cost per efficiency was the best method because it is the most impact per dollar. This selection may not be as financially justifiable in the short term as some of the more bare bones options, but in the long term, much less energy will be lost from the solar panels, which will lead to a larger savings. Also, higher quality parts will have a greater reliability, so future repair costs will be lessened. Furthermore, this efficiency will be better for the environment in the long term because less of the energy from the solar panels will be lost, so less solar panels will be needed in order to get the required 120 megawatt hours. The combination of these factors leads us to using this cost per efficiency method of selection.
For Project 2, the engineers of Team 67 decided to generate the program required to replicate the results corresponding to those of the model validation, as well as a program to find the optimal solution to the situation and context. In preparation for accomplishing these tasks, the engineers of Team 67 engaged in extensive research and organization to plan the critical components necessary to develop the required software. This process involved utilizing a flowchart to plan the logic of the programs, deriving the mathematical expressions relevant to describe the behavior of the physical model, and outlining an appropriate universal accounting equation to track the energy of the system at any given point. Following the finalization of this preparatory process, the engineers of Team 67 began to generate the programs required to replicate the results corresponding to those of the model validation, as well as optimize the solution to the situation and context. At this point, the programs responsible for accomplishing these tasks will be discussed, and following the conclusion of this discussion, these programs will be demonstrated. The first program is a Python file referred to as Proj2 Solar Hydro Team 67, which requests and receives the necessary model specifications from the user to calculate and display the relevant results for the given situation provided. To accomplish this task, this script imports the file referred to as Proj2 Functions Team 67, which contains all the relevant user-defined functions necessary for the main script to execute properly. Following this aspect of the code, the script defines the various given constants and requests and receives the specific model specifications desired by the user, storing these values in the appropriate variables to be passed as arguments to the relevant functions for the remainder of the script. At the conclusion of this aspect of the code, the script calls the relevant functions in the logical order, passing the required variables as parameters to the corresponding functions, and returning the results to the appropriate variables. At the completion of this aspect of the code, the script formats and displays the relevant information to the console, allowing the user to view the results of the model specifications describing the situation provided. The second program is a Python file referred to as Proj2 Analysis Team 67, which executes independent of user interactions and displays the optimal solution for the situation and context, following consideration of every possible combination of parameters available for selection. To accomplish this task, the script imports the math library and matplotlib library,
as well as the file referred to as proj2 analysis functions team67, which contains all the relevant user-defined functions necessary for the main script to execute properly. Following this aspect of the code, the script defines the various given constants and establishes various lists consisting of every possible parameter available for selection. Additionally, the script defines empty lists responsible for tracking the parameters selected and results determined for every iteration of the script, as the program explores every possible combination of parameters available for selection in an attempt to identify the optimal combination of parameters to select. At the conclusion of this aspect of the code, the script displays 4 subplots and a figure to provide a visual representation of the efficiency and cost of the system for every possible combination of parameters available for selection, and determines the optimal parameters to select in order to maximize the efficiency of the system with respect to the cost of the system. Furthermore, the script displays the relevant information for the console, allowing the user to view the specifications of the optimal model, as well as the results of the optimal model specifications describing the situation. At this point in the discussion, the engineers of Team 67 are proud to demonstrate the programs generated. This demonstration will begin with the execution of the script responsible for determining and displaying the specifications of the optimal model, as well as the results of the optimal model specifications describing the situation, and will conclude with the execution of the script responsible for determining and displaying the results of the model specifications, which will be equivalent to those of the optimal model in an attempt to validate both models.